Mechanics with Newton's laws. Here we're going to focus on two of Sir Isaac Newton's laws. The second law states that force equals mass times acceleration. But when we're going to use this law, we're actually going to treat force as a vector and split up the force components into their horizontal and vertical components. And there might be more than one force in these directions, and we need to take into consideration all of them. So we're actually going to rewrite this formula as the sum of the forces in the x direction will equal mass times acceleration, and the sum of the forces in the y direction will equal mass times acceleration. It should be in the x direction and the y direction. So something we're going to need to do is break up the forces and resolve them into their x and y components. We're also going to look at Newton's third law, which states that every force has an equal and opposite force. So if we have some body sitting on a surface with some weight, it will apply an equal and opposite force in the direction perpendicular to the surface, which we call the normal force. So using these concepts, we're going to give some questions a go and see what happens. So the first question states that we have a particle of mass 2 kilograms and this particle is acted on by a force whose direction is constant and magnitude is given by 10t squared minus 4t cubed. So let's start to draw a diagram of what's happening. So let's say we've got some particle of, I should say some object of mass 2 kilograms, and a force is being acted on it in the direction of motion. So let's say it's moving this way with some velocity v. So the force is in the same direction as the motion, and that force is equal to 10t squared minus 4t cubed newtons. So force is measured in newtons. And we know initially, so when t equals 0, the object has a velocity of 5 meters per second. And we want to find the velocity after 3 seconds. So we want to find the velocity after 3 seconds. And we know we have some kind of weight force, because any weight force is equal to mass times gravity. And if its mass is 2, we can say the weight force is equal to 2g. And we have an equal and opposite force here, our normal force, n. Now, here we want to use Newton's second law to sum the forces in one of the directions. And since we're interested in the velocity after 3 seconds about time, we're more interested in this horizontal force here. So we know if we sum the forces in the x direction, it will equal mass times acceleration in the x direction. There's only one force in the x direction, so we don't need to sum it with anything else. And we always take into consideration the direction of movement, and that will be our positive direction. So if the object's moving this way, anything going this way will have a positive value. So that the force of 10t squared minus 4t cubed will be positive. It will equal mass times acceleration in the x direction. So its mass is 2, and we're just going to write our acceleration as a here, but it's acceleration in the x direction. Now let's go ahead and make A the subject. So we'll get A equals, we'll just divide everything by 2, we'll get A equals 5t squared minus 2t cubed. And remember, we're after the velocity when time is equal to 3. So we need an expression for the velocity. So we're going to go ahead and change our A. We're going to write A as dv dt, and this equals 5t squared minus 5t cubed. And we can go ahead and integrate both sides here. And a good trick here is, instead of dealing with a constant, we can add some clever bounds in to our integral, so we don't have a constant. So on our left-hand side, we're dealing with velocity, and we know the initial velocity is 5, and it gets to some velocity v. And we know on the right-hand side, our initial time was 0, and then it gets to some time equal to t. And this will just help us not get a constant. So the integral of the left-hand side is equal to v, bound between v and 5. The integral of the right-hand side, we're going to get 5t cubed all over 3 minus 2t to the 4 all over 4, bound between 0 and t. So just again, these lower bounds are our initial conditions, and the upper bounds are some just general expressions for v and t. So we can go ahead and sub those in. Subbing in v, we'll get v, minus subbing in 5 for v, we'll get 5, equals subbing in t, we're just going to get 5t cubed minus 3 minus, the 2 over 4 will simplify to 1 on 2, so we're just going to get subbing in t for t, we're just going to get t to the 4 on 2, minus subbing in 0, we're just going to get 0, and then we can add the 5 to the other side, so we'll get 5t cubed all on 3 minus t to the 4 on 2 plus 5, and we have our expression for velocity as a function of time, and we want to know the velocity after 3 seconds. So all we need to do now is sub in 3 for t. So we get v equals 5 times 3 cubed, all on 3, minus 3 to the 4 on 2 plus 5. And evaluating all this gives us 19 over 2 meters per second. Going to have a look at another example. If we have a ceiling and some weight with a mass of 10 kilograms, it's going to be hanging from that ceiling with 2 ropes, so one attached up there and one over here. I'm going to say this is point A, this is point B, and we'll call this point P. Call this point C. This angle is equal to 30 degrees. And we know the ratio of BP to AP is 3 to 2. We're after the tension in the string AP and BP, after the tension in the strings. Now, in order to find the tension in the strings, we should draw what's called a free body diagram, where we're just focusing on the forces involved here. So we're going to do those in red. So we know we have some kind of weight here, and the weight is equal to mass times gravity. So we know the mass is equal to 10, and we'll let gravity be g. And we have the tension acting up this string over here, and the tension of this one acting along the string here. when we're looking at diagrams where we have forces acting on an angle, those forces always need to be resolved into their x and y components. So if we let the tension in AP be T1 and the tension in BP be T2, we'll be able to resolve these forces. To reference some angle over here, we need to find that angle first. So let's go ahead and do that. So we know we can write some expressions. We can write that sine 30, so this is using triangle CBP. Sine 30 is going to be our opposite side, which is CP, over our hypotenuse, which is BP. And we know that sine theta, so using triangle CAP, is going to be also equal to CP over AP. If we make CP the subject in both, we'll have CP equals BP sine 30 and CP equals AP sine theta. Let's go ahead and divide these equations with each other. We're going to this equation 1 and this equation 2. We're going to do 1 divided by 2. So we're going to have CP equals BP sine 30 for equation 1 over CP over AP sine theta. CP on CP will be 1. We know BP on AP, using the ratio given in the question, is 3 on 2. We know sine 30 is a half, and it's over sine theta. So let's multiply both sides by sine theta. We have sine theta equals 3 on 2 times a half. So we know sine theta equals 3 on 4, which means theta has to be the inverse sine of 3 over 4, which we can leave it like that. Now we're ready to resolve our forces for T1 and T2. So resolving them means drawing our horizontal and vertical components in, so they form a nice rectangle. We have this one here and this one here. So these are both vertical, we just didn't want to draw them on top of each other. We know the angle in here is 30 degrees from alternate angles, and this one is also equal to theta, also from alternate angles. The horizontal component of the force, of this force over here, is going to be T2 cos 30. And if you can't see that, you can always take it a bit slow. So if this is 30 degrees, and we're treating the hypotenuse as T2, and we want to know the x component, we can write an expression that cos 30 equals the adjacent side over the hypotenuse, and timesing both sides by T2, we're going to get x equals T2 cos 30, which is exactly the x component there. And in a very similar way, the y component up here will be T2 sine 30. The x component of T1 will be T1 cos theta. And the y component of T1 will be T1 sine theta. And now that we've broken it up into their x and y components, we're ready to sum the forces in either the x direction or the y direction. And we're going to need to do both. Now, we know that, let's look at the x direction first. We know summing the forces in the x direction will equal mass times acceleration in the x direction. But this scenario involves no movement because we have a ceiling with a weight hanging with two ropes. So this means if there's no movement, it means the acceleration is equal to 0, and it means the sum of the forces will also equal 0. So now we just want to sum the forces in the x direction. And there's only two of them. There's only the T1 cos theta and T2 cos 30. They're the only ones acting in the x direction. And we need to define a direction to be positive. And we'll just define our normal xy axis here. So anything to the right will be positive and anything upwards will be positive. So that means the T2 cos 30 will be positive and T1 cos theta will be negative, but we know theta is equal to the inverse sine of 3/4. And the sum of these two forces equals 0 because there's no movement. So now let's look at summing the forces in the y direction. And this is also going to equal 0 because again there's no movement in this system. This time we have three forces in the y direction. We have the two, one for each of the tension in the string and also the weight force in the y direction. Remember that we're not considering this angled force since all it is the horizontal and vertical components. They replace the horizontal force. So summing the force in the y direction, we've defined anything acting upwards as positive, which means these two forces are positive and this one is negative. So we're going to get T2 sine 30 plus T1 sine theta, which is the inverse sine of 3/4, minus 10g, all equals 0. And now we just have two equations with two unknowns which we need to solve for, so we can leave them in terms of g. So let's go ahead and solve these two equations simultaneously. So we had T2 cos 30, which is just root 3 on 2, minus T1 times cos of inverse sine of 3 on 4 equals 0. And we had T2 sine 30, which is just a half, plus T1 times sine of the inverse sine of 3 on 4, which is just 3 on 4, minus 10g. We're going to use g as 9.8 to actually get a value, and that all equals 0. So this second equation looks a little bit nicer to deal with, so we'll deal with that. So we're going to get a half T2 plus 3/4 times T1 minus 98 equals 0. So we want to go ahead and make T2 the subject. We can make T1 the subject, it wouldn't matter. So we're going to make T2 as the subject. So we're going to get a half T2, move everything to the other side, so we'll get positive 98 minus 3/4 of T1, and we'll times everything by 2, so we'll get T2 equals 196 minus 3 on 2 T1. Now we're just going to go ahead and sub that into our first equation. So we're going to get, we know T2 is equal to all this, so we're going to get 196 minus 3 on 2 T1. So we're subbing this in for T2 into this equation here. That's all going to be multiplied by root 3 on 2 minus T1 cos of the inverse sine of 3 on 4 all equals 0. Let's go ahead and expand this bracket out. So we're going to get 98 root 3 minus 3 root 3 on 4 T1 minus T1 times cos of the inverse sine of 3 on 4. Let's take both our t1 terms to the other side since they're both negative. So we'll get 3 root 3 on 4 t1 plus t1 times cos of the inverse sine of 3 on 4, all equals 98 root 3. We'll factor out the t1. So we get 3 root 3 on 4 plus cos of the inverse sine of 3 on 4, all equals 98 root 3. Dividing both sides by the bracket, we're going to get t1 equals 98 root 3 over 3 root 3 on 4 plus cos of the inverse sine of 3 on 4. And that we can all put in the calculator, and we'll get T1 is equal to 21.65 newtons. And there's the tension in the first string. And from here, we can just sub this T1 into this equation here to get T2. So we know T2 is going to equal 196 minus 3 on 2 times 21.65. And plugging all that in is going to give us T2 being 16.53 newtons. And there's the two tensions in the strings.